One of the things I enjoy most about science is that sometimes the most important discoveries begin with something that doesn't make sense. Imagine you have a huge jigsaw puzzle, and every piece is falling into place, except for one, and no matter how many times you look at it, it refuses to fit. For decades, climate scientists had a puzzle just like that. As greenhouse gases increased, and much of the world's oceans steadily warmed, there was one region that seemed to be telling a different story: the Southern Ocean surrounding Antarctica. For years, it warmed much more slowly than scientists expected. In some places, it even showed periods of cooling. So what was different about Antarctica? A new study may finally provide an answer, and ironically, it may have not even been the ocean at all. Today, we're exploring the Antarctic paradox. Welcome back to the podcast. I'm Dr. Mack, and this is the Climate Translation. I want to start with a question. How many of you remember hearing about the ozone hole growing up? As someone who grew up in the 70s and 80s, it was everywhere. On the evening news, newspapers, and science class. There were even public service announcements about protecting the ozone layer, and governments around the world began phasing out chemicals called chlorofluorocarbons, or CFCs. For many of us, the ozone hole became a defining environmental story. These were not chemicals invented, though, with the intention of harming the atmosphere. When they were introduced, they seemed ideal. They were stable, they weren't toxic under normal conditions, and they weren't flammable. That made them great for dangerous chemicals that were previously used in refrigerators and air conditioners. Over time, CFCs appeared everywhere. They were put into aerosol cans. They were used to create foam insulation and packaging. Some were even used as solvents for cleaning electronic equipment. Their stability was one of the qualities that made them valuable, but it was also a source of their problem. Because CFCs don't break down easily at the surface, they remain in our air, and they actually slowly travel up into the stratosphere. Once there, intense ultraviolet radiation from the sun can break the molecules apart and release chlorine. That chlorine could then participate in additional reactions that destroyed natural ozone. And it wasn't just finished after destroying just one ozone molecule. A single chlorine atom could continue destroying ozone again and again. So a chemical released from a refrigerator or an air conditioner or an aerosol can at the ground could eventually affect the atmosphere miles above us. And that delay also made the danger harder to recognize. Ironically, this environmental issue became a major public concern around the same time scientists began to warn us about global warming. And because the two of them became linked together in people's minds, it caused a problem. In fact, a survey conducted by researchers at Yale University found that 61% of Americans believe that the ozone hole was the cause of global warming, and 43% thought that repairing the ozone layer would slow climate change. It's a completely understandable conclusion to reach. After all, both involve human activities changing the atmosphere, and both became scientific concerns at around the same time. To make things even more confusing, some of the chemicals that damage the ozone layer are also powerful greenhouse gases. So it's easy to assume they're simply part of the same problem, but of course they're not. They're two distinct environmental challenges that just happen to interact in some fascinating ways. The ozone layer sits high above us in the stratosphere. That's about 10 to 30 miles above the Earth's surface. I like to think of ozone kind of like the Earth's sunscreen. It absorbs much of the sun's harmful UV radiation before it reaches the ground. This protects living things from levels of UV light that would otherwise be dangerous. We're not just talking about sunburns here. We're talking about cancer or worse. Global warming works very differently. Instead of UV, it involves infrared energy, the heat that the Earth is constantly trying to radiate back into space. Greenhouse gases like carbon dioxide and methane absorb some of the heat that's outgoing and re-radiate it back down, making the lower atmosphere warmer. So while the ozone layer is like a sunscreen, greenhouse gases are like an extra blanket. They both influence the planet, but they do so in different physical ways. And that's what makes today's story so fascinating, because even though they're separate environmental problems, they unexpectedly influence each other. And the first sign of that influence appeared high above Antarctica, where the loss of ozone caused the stratosphere to become cooler. Now, you heard me right. In an age of global warming, we've actually seen the stratosphere become colder over the southern part of our planet, as ozone was depleted. To understand why, we need to remember what ozone actually does. Ozone absorbs UV radiation from the sun, and when it absorbs that energy, it warms the surrounding air. So when large amounts of ozone were lost over Antarctica, less UV energy was absorbed to the stratosphere, and with less being absorbed, that part of the atmosphere cooled. Now, at first glance, that might not seem like a big deal. After all, we're talking about air at 10 to 30 miles above the Earth's surface. How could something happening that high up possibly influence the surface below? The answer comes down to one of the most fundamental principles of meteorology. The atmosphere responds to differences in temperature. When air becomes colder, it becomes dense and contracts. When air becomes warm, it becomes less dense and expands. Across large distances, those temperature differences affect pressure patterns at different heights in the atmosphere. Differences in pressure help create wind, and when the temperature contrast becomes extreme, winds become stronger as well. In this case, the unusually cold stratosphere over Antarctica increased the temperature contrast with other regions in the southern hemisphere, places like South America, Africa, Australia, and their surrounding oceans. As that contrast increased, the powerful west to east winds that circulate around Antarctica strengthened and shifted farther towards the pole. Meteorologists call this ring of winds the polar vortex, and you've probably heard the phrase before in winter weather forecasts. In the northern hemisphere, we also have a polar vortex, and it can weaken or become distorted. That can release cold Arctic air south into North America, Europe, and Asia, and supply the conditions that can make severe winter outbreaks possible. But in the southern hemisphere, it's a little different. Because Antarctica is surrounded almost entirely by flat ocean, with few mountain ranges and continents to disrupt the circulation, the polar vortex is generally more stable and nearly circles the continent like a giant atmospheric racetrack, racing around and round without stopping. So as the stratosphere cooled, those winds became stronger and stronger and then shifted closer to Antarctica. And that's where the atmosphere began talking to the ocean below. The stronger winds changed how the surface water moved around the continent. That influenced where cold water spread, where deeper water rose to the surface, and how heat was exchanged between the ocean and the atmosphere. In effect, it masked the effects of global warming that scientists were expecting to see at the surface. The greenhouse effect did not disappear. It was still adding energy to the climate system. But in this particular region, another human-caused influence was changing the winds and redistributing ocean heat at the same time. And so for many years, while much of the global ocean warmed, parts of the southern ocean warmed more slowly and at times even cooled. It baffled scientists for a long time. Surely greenhouse gases had not stopped working there. something else had to be altering how the region responded. It was a paradox. But over time, better satellite observations, ocean measurements, and climate models allowed researchers to build a clearer picture of what was happening. And once scientists began to suspect a connection, they had to answer a question. How could they prove it? So scientists had a hypothesis. They suspected that the ozone hole had strengthened the winds around Antarctica, and those stronger winds had changed how the Southern Ocean moved heat. But suspicion isn't proof. In science, you have to test your ideas. So how do you test something you can't recreate in a laboratory? Well, you build a computer model. Imagine you build two identical worlds in a simulator. You give them the same landforms, the same atmosphere, the same ocean currents, the same amount of sunshine. The only difference is, in World A, you turn off its ozone layer, and in World B, you leave the ozone perfectly healthy. Then you observe the weather patterns. Do they drift apart? If so, you've learned something about exactly what ozone does. Climate scientists did something similar, but with a lot more complex calculations. They began with models that included a lot of other things in the Earth's climate: greenhouse gases, volcanoes, wind currents, changes in the sun's energy, seasons, ocean circulation, and among others, yes, the ozone layer. Then they changed only one variable. In this case, they ran simulations that included a loss of ozone over Antarctica. And they ran many simulations comparing each other, where the ozone layer remained unchanged and where it was in various stages of loss. Everything else remained the same. And the models began to show that ozone depletion produced stronger winds around Antarctica and a cooler Southern Ocean, while the other models did not. It was powerful evidence that ozone loss was playing an important role. But scientists didn't stop there. A computer simulation by itself is not enough. You have to match what's actually being observed. So researchers compared their simulations with decades of measurements from satellites, weather balloons, ships, ocean buoys, and other observations collected around Antarctica. The pieces came together. Everything matched. The wind changes matched. The pattern of cooling in the Southern Ocean matched. The paradox seemed to have been solved. We didn't get there through a one big aha moment, though. That's not how science works. Instead, it was about stacking up dozens of independent clues until a conclusion became impossible to ignore. It cleared up a mystery that had stumped climate scientists for decades. But solving one puzzle often hands you a new one. If the ozone hole was acting as a temporary shield against the heat, what happens now that the ozone layer is healing? The story of our ozone hole begins with one of the greatest environmental success stories in modern history. Once scientists discovered that CFCs were damaging the ozone layer, countries around the world did something remarkable. In 1987, they adopted the Montreal Protocol. Nations that disagreed on other issues came together with a common goal: to phase out chemicals destroying the ozone layer. And it worked. Measurements collected over the past several decades show that the ozone layer is gradually recovering. The Antarctic ozone hole still forms each spring, but scientists are continuing to expect it to shrink over the coming decades as the atmosphere slowly removes the remaining CFCs. That's worth celebrating. It demonstrates something important about science. Scientists identified a problem, they uncovered a cause, and the world responded. The atmosphere began to heal. That's exactly how we hope science and society work together. But here's where the story takes a twist. Remember that the cooling of the Southern Ocean wasn't caused by the ozone hole directly. It was caused by changes in atmospheric circulation that the ozone hole created. As the ozone layer recovers, those changes are going to weaken. The exceptionally strong winds around Antarctica are expected to gradually relax towards a more typical state. and as they do, their cooling influence on the Southern Ocean will fade. That means global warming becomes more evident. It won't happen overnight, but scientists are expecting the Southern Ocean to increasingly resemble the warming trends already observed across the rest of the world's oceans. And that raises some important questions about what comes next. Let's start with ice. Sea ice floating around Antarctica doesn't raise sea level when it melts, just like melting ice cubes in a glass of water don't cause it to overflow. But law still matters. Sea ice reflects sunlight and it insulates the ocean from the atmosphere. It provides a habitat for Antarctic ecosystems, and it creates a cold, salty water region that can sink into the deep ocean. A warmer ocean can make it harder for that ice to form and easier for it to melt. The larger concern for sea level is the ice on land. Much of Antarctica's land ice reaches the ocean through enormous glaciers. In many places, those glaciers flow into ice shelves extending outward from the continent. Those shelves act like braces. They don't stop the ice behind them from moving, but they slow its journey. If a warmer ocean melts those braces, the glaciers can then move into the sea faster, and ice from the land can add to global sea level. Near the continent, extremely cold and salty water sinks to the ocean floor. This bottom water spreads across the Atlantic and Pacific and Indian Oceans and helps ventilate some of the deepest part of the global ocean. But melting land ice adds fresh water. Fresh water is less dense, so it doesn't sink as rapidly. That means greater melting could weaken the production of deep water, altering the slow overturning circulation that moves oxygen, carbon, and nutrients throughout our oceans. Then there's the atmosphere. The winds surrounding Antarctica help influence storm tracks and rainfall across the southern hemisphere. When those winds strengthen, weaken, or shift north and south, the effects can reach parts of Australia, southern Africa, South America, and the surrounding oceans. That does not mean ozone recovery alone will determine the weather in those places. Greenhouse gases, ocean temperatures, tropic variability, and year-to-year changes will continue to play a role. But if the circulation around Antarctica changes, the pathways followed by storms and moisture may change. Over the next century or two, Antarctica will not simply respond to one influence. Ozone recovery will be occurring while greenhouse gases continue to warm the atmosphere and the ocean. Sea ice will interact with changing winds. Melting land ice will add fresh water to our oceans, and those changes may feed back into changes in ocean circulation and the atmosphere above it. We cannot describe every detail of that future with certainty. How much changes or how quickly will depend heavily on how much warming occurs. But the Antarctica our descendants experience 1 or 2 centuries from now could operate very differently from the Antarctica scientists began observing during the 20th century. The paradox helped hide some of that change for a time, but as it fades, we may begin to see more clearly just how sensitive the southern edge of our planet really is. Antarctica once appeared to be resisting part of the warming seen around the rest of our planet. Now we understand that the ozone hole wasn't stopping climate change, but it was temporarily changing the winds and ocean circulations around the continent. As the ozone layer heals, that influence will fade, revealing a southern ocean entering a very different future. The Antarctic paradox was never that global warming had failed. It was another human-caused change that had briefly hidden parts of the signal. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate that you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.